Okay, so welcome back, everybody. So I had finished yesterday with a example of uh, how we need to consider branch cuts and whether or not, say, a contour that we're integrating on crosses one, or more generally, just whether a contour we're integrating over crosses through any problematic points, right? Um, So one common example of that is crossing a branch cut that's involved in defining some multi-valued function that is involved with the integrand. Okay, and so I wanted to do one more example of that before we'll see more examples of those considerations when we get to talking about antiderivatives in our fundamental theorem that we're going to discuss a little bit later. So, so here's one more example of that. Let C be the positively oriented. And remember, uh, this means the counterclockwise orientation. So let C be the positively oriented circle that we'll say is a circle of radius r centered at the origin. So this is r e to the I theta, where theta is between minus pi and pi. Okay, and let A be any non-zero real number. Okay. So importantly here, A is not necessarily an integer or a natural number. So it's just any non-zero real number. And so because of that, if we have an exponential function involving this A as an exponent, we have to use our definition involving involving the exponential function in the log in order to actually define this thing. Okay, so I want to compute the contour integral over the C of z to the a. Or we'll say z to the a minus 1 dz. Okay, we would be happy to compute this in the same, or z to the a just as well. So I want to compute this thing. So, okay. Now, because a is just non-zero real number, when I define this integrand function z to the a minus 1, it's not as simple as just this has a very specific definition that we mentioned before, which is that this is defined as e to the a minus 1 log z, right? And so if we take, say, principal branch here, so this is the fact that I'm taking the principal log here means I'm taking the principal branch of this thing. So the principal branch of this is, I have modulus of z is positive, and the argument of z is the principal argument, okay, which of course is strictly between pi and minus pi. Okay, so this is the principal branch, right, of that function. So this is the principal branch of z to the a minus 1. Okay, it's always good to remind yourself that even something that looks like this, you might feel is innocuous when you're dealing with real valued functions, is something that we have to take caution with here. Okay, and so I want to compute this contour integral. Now, what is the problem with just going ahead with this, right? Well, there's this slight problem where if I draw in my circle, so my circle of radius r centered at the origin looks like this. Right, here's what my circle C looks like. But this principal branch, of course, has an issue. It has a branch cut where, well, here is my three parts of the axes that is okay, but the origin itself is actually a branch point here, okay, and the negative real axis here is a branch cut. Okay, and so for instance, right, my curve C definitely crosses this branch cut here, right? So my C is not crossing this branch point. It's not going through there at all, so that's not an issue. None of these other points are an issue, but if I'm wanting to integrate along this whole contour, I have an issue here at this point because this integrand, right, is actually technically not well defined here, right? Okay, if I wanted it to be well defined there, I'd have to take a different branch, and then of course it wouldn't be well defined somewhere else, which is exactly why we want to address this here, right? Because the curve in itself is, well, it's a circle, so it's going to give us issues wherever we take this cut, okay? And that's why we want to talk about this. So, you could say, well, couldn't you use a different curve? Well, yeah, I could use some other curve, and I could do that contour integral just fine without having to worry about this, but I want to address this specifically because suppose you really, really want to do this contour integral about this specific curve, right? So we gotta talk about how we would do this. Okay, so as with the usual case, first things first, when you're doing a contour integral, you need the parameterization, right? You need the representation of C. So here, what is a good parameterization to use? Well, we already have Z in terms of theta, right? And so Z is equal to Z of theta, where Z of theta is just R e to the I theta, right? So Z of theta is R e to the I theta here, which of course, using Euler's formula, this is you can think of this as R cosine theta plus I times R sine theta. Okay, so here's our representation for C. Of course, theta lives in minus pi to pi. Okay, so your parameterization, you also have to have your window where your parameter lives, of course. Okay, so then if we are actually going to compute this, I have to write out the integrand that shows up in the definition, right? And so my so f of z is z to the a minus 1. So then I want to compute what is f of z of theta times z prime of theta. Okay, well, since on the previous page I wrote out that z of theta is r e to the I theta, the question is what's z prime of theta? So z prime of theta, that's the derivative of z of theta with respect to theta. What is that? So that is r e to the I theta times I, right? So this is I r e to the I theta. Okay. And so this quantity is, so I'm taking z of theta, raising it to the a minus 1. So this is r e to the I theta to the a minus 1 times I r e to the I theta. Okay. And so this would be r to the a minus 1 times r, so that's going to be r to the a. The I is going to carry over. This is going to be I r to the a times e to the I times a minus 1 theta. But here I'm going to have I theta. So this is e to the I a theta. Okay. Let me, I have a slight disagreement with, there we go, with my camera and the orientation of my paper, so it was confusing me. Okay. So this is my integrand. Of course, I can use Euler's formula here to make this. I can put this in terms of sine and cosine. So this is minus, since we're multiplying by I here, the real part of this is going to be minus R A sine of A theta plus I R to the A cosine of A theta. Okay. All right. Okay. Now R is a real number, so R to the A here, right, could be like A could be 1/2, right, or 2/3, or 5/4 or something, right? It could be any of those things, and so that it could technically involve roots, right? It could involve like fourth roots or square roots or whatever, and so this itself could be multi-valued. So to fix that, we're going to take the positive values of R. So taking positive values of R to the A, right? Again, remember A is just a non-zero real number, so A could be 1/2, for instance. Okay, so we have to address that. Okay, so this is actually piecewise continuous on the open interval minus pi to pi. Okay, and so our integral exists, and to see that it exists, this integral over c of z to the a minus 1 dz is equal to, I can pull out an I r to the a here, so this would be I times r to the a times the integral from minus pi to pi, okay, of e to the I a theta d theta, okay, which is so I know how to do this integral. So this is I r to the a here times the integral the integral of e I to the a theta. This is just going to be e I to the a theta over I times a, right? So this is e I to the a theta over I times a, and this is going to be evaluated from minus pi to pi. Okay, and so this is going to be, so here, rewriting this, so I can write this in a convenient way here. So one, I'm going to introduce, so I'm going to multiply this by 2 over 2. And the reason why I'm going to do this is so that I can write this in a particularly nice way. So you'll see why I'm doing this here in a second. So multiplying by 2 over 2, I'm going to turn this in. I'm not going to cancel the i's yet. So this is going to be I times 2 r to the a over a times, evaluating this, this is e to the ia pi minus e to the minus ia pi over 2 times I. Okay. Which gives us the following, right? The reason I wanted to multiply by 2 over 2 here is that this quantity now is something that I can immediately recognize as sine of a pi, right? So this is I 2 r to the a over a times sine of a times pi. Okay. All right. So this is the value of this contour integral. Now, to see some specific values of this thing, okay, when we take a to be, say, some specific, so some specified real numbers, if we set a to be, say, for instance, integers that are not non-zero, or that are non-zero, we can immediately tell the following. So maybe I'll write this on another sheet so that I have room. Note, if a is any integer and a is non-zero, then we'll write a as, we'll say, a is equal to n, some non-zero integer. Then what we've just shown is that the contour integral of z to the n minus 1 dz is equal to I times 2 pi, or sorry, 2 r to the n over n times sine of n pi. But this is an integer multiple of pi now, and this is 0. Okay, so even though this circle, right, this closed contour crossed a branch cut for my integrand function, this thing is still 0 on this closed contour, right? And of course, it didn't actually matter what the radius was, right? So it didn't actually matter what the radius was. This was still the case. Okay. All right. So just to repeat, it didn't matter what the radius of our circle was, right? This contour integral of this function z to the n minus 1 is still 0, right? Also, note, if a is equal to 0, right? If a is equal to 0, then the thing that we're computing is the contour integral of z to the minus 1 dz, or rewriting that in a form that you're used to. It's the contour integral of 1 over z dz. Well, this is then the integral from minus pi to pi of 1 over r e to the I theta times I r e to the I theta d theta. Okay, and I can pull this I out. So this is I times the integral from minus pi to pi of these things cancel, and so this is just d theta. So this is 2 pi I. Okay. All right. So, a couple of things to say here. Okay. This is going to be a useful, so one more note here on this page. This is a useful example that illustrates some key properties that we'll discuss when we talk about antiderivatives. right? So namely, the differences between these things. So this thing was always 0 uh, whenever you took this contour to be a circle of any radius centered at the origin. But you might be convinced that if I'm allowed to take circles of any radius, right, centered at the origin, then maybe, it stands to reason that it didn't really matter that those were circles I was taking, right? Maybe any closed contour taken in this way, I would get the same result. Okay. But we won't see exactly how this all works out until a little bit later. Okay, but this is a good example. We're going to be returning to this because it's going to illustrate basically exactly what's going on. Okay. So now we're interested in not just estimating, or not just actually computing the value of a contour integral, but actually estimating its value. So putting, say, an upper bound on its value. So sometimes we are interested not in simply computing a contour integral, but also in estimating its value, or putting an upper bound on its value. And the reason this is important, of course, is because you know that sometimes integrals are hard to compute. Right? So sometimes they're hard to compute, but even if we computed them, we're actually not just so we're not simply interested in maybe saying something about a particular contour integral, but maybe a class of contour integrals, or maybe we're just interested in not the specific value itself, or we just want to know that it is within some bounds. Okay, and so ultimately our goal is to come up with a way of bounding. So goal is to bound this quantity in some way dependent on f of z. Right. So and what I mean by that is we need conditions on f of z to make this work in general. All right, which you might expect something like that. Okay. And so in order to do this, there's the lemma, and this lemma is going to be used in the proof of the main fact that we're interested in here. And so the lemma is the following. So if we have a complex valued function of a real variable, w, so if w of t is a piecewise continuous complex valued function on a to b, this closed interval, then the modulus of the integral from a to b of w of t dt is less than or equal to the integral from a to b of the modulus of w of t dt. Okay. Now you may remember you may remember inequalities involving passing absolute value signs underneath an integral in this way from your real analysis experience. Okay. This fact is do similarly to that. We just kind of have to do some bookkeeping here. Okay, so I'm actually not going to prove the lemma. I'm just going to state the theorem that this uses. So we use this to prove the following theorem. Here is our main result from this chunk of material. So let C denote a contour with length L. Okay, so this contour has arc length L. Suppose that a function f of z is piecewise continuous on C. Okay. If f of z satisfies the following inequality, that its modulus is less than or equal to m for some non-negative constant m. So if this is satisfied for some non-negative constant for all z on C, then the modulus of this contour integral of f of z dz can be no greater than the bounding constant for f times the length of the contour L. Okay. Okay. So this is our big fact. Now, let's prove this using that lemma. Okay. Well, let z be the parametric representation of C. So z is z of t. T is in the closed interval a to b. Right? Then by that lemma, this modulus of f of z dz, by definition, this is just equal to the modulus of the integral from a to b of f of z of t times z prime of t dt. And by the lemma, this thing is less than or equal to the integral from a to b of the modulus of what's inside, f of z of t times z prime of t dt. Okay. But we have the following, that if I look at the modulus of this integrand in the definition for contour integral, well, this is the this is the same as modulus of f of z of t times the modulus of z prime of t. But f of z of t, whatever this thing is, we know that f satisfies this bound. This is less than or equal to m, so this is actually less than or equal to m times the modulus of z prime of t. Okay. So then slapping integration signs on either side of this thing, right, coming down here, this thing is less than or equal to the integral from a to b of m times the modulus of z prime of t dt. But this is just equal to m times the integral from a to b of the modulus of z prime of t dt. But this is the definition of the length of C. So this is M times L. And that's it, right? So that's it. Okay, so really the proof of this theorem just relied on that lemma entirely. Okay. Okay. And so, why are we happy with this result? Because this seems like a very restrictive thing. Okay, this seems like a restrictive condition. So why are we happy with this result? So that's a good question. Maybe I'll write that down. Why are we happy with this? I.e., isn't the condition that our function be bounded in this way, i.e. f be bounded on C, very restrictive? The answer is that since f is piecewise continuous on C, right? So since f is piecewise continuous on C, this number will always exist. Why? Because this has to do with the fact that, I shouldn't draw this implication error. So this has to do with the fact that this function, the modulus of f of z of t, is continuous on the real interval a to b when f is continuous on C. Okay. So we have a real valued function that is continuous on a closed and bounded subset of the reals. A closed and bounded subset of the reals is compact. Okay. And a continuous function on a compact set always attains its maximum. The image of such a set is also compact. But the easiest way to remember this is that we have what's called the Max Min Theorem. So Max Min Theorem, okay, it might not always be called this. Max Min Theorem for real functions says such an m exists and this m is attained somewhere on the interval a to b. Okay. So we've passed a continuity here, but this is actually true even when we're talking about piecewise continuity. Okay. And so actually you're using this Max Min theorem that you knew all the way back in Calc 1. You even did a version of this in Calc 3. There was a min-max theorem. That was the reason why you could assume on closed and bounded set, say in the plane, that you could always begin the Lagrange multiplier process, right, for functions of more than one variable. Okay, so this is good. This tells us that we can always find something like this. The curve itself is a closed and bounded set in the plane, and that's what allows us to do this. Okay. And so I have the following example. Let C be the arc of the circle modulus of z is equal to 2 from 2 to 2i. There, I'll write this as z equals 2 to z equals 2i. Okay, that lies in the first quadrant, right? Okay, so just quickly, here's z equals 2, and here's z equals 2i. Okay, and here's my c. All right, this is my orientation on it. Okay. All right. What if I want to say compute or to find a bound, right? A maximum value for this integral of say z plus 4 over z cubed minus 1 dz. So I want to find a bound here. Okay, how can I do that? Okay, so well, first I note that if I look at the modulus of z plus 4, right, here comes the kung fu portion of the class, where if you recall, early on, when your first homeworks asked you about some inequalities involving complex numbers like this, where if, for instance, you were on the circle modulus of z is equal to 2, then using the triangle inequality, we know that this modulus of z plus 4 is less than or equal to the modulus of z plus 4. Okay, but since modulus of z is equal to 2, this is 6 here. And so modulus of z plus 4 is less than or equal to 6, right? So all those things you were asked to do had purpose. It wasn't just mindless algebra to, kind of just for no reason. This was grinding it into your muscle memory. Okay. Similarly, if I look at this thing, right, again, by those related inequalities to the triangle inequality, this was greater than or equal to the modulus of, or the absolute value of the modulus of z cubed minus 1, right? But this is 8 minus 1, so this is 7. Okay. And so what is going on here is that if I look at this ratio, right, so z plus 4 over z cubed minus 1, okay, this is, of course, modulus of z plus 4 over modulus of z cubed minus 1. Let's make sure that the signs are going to go in the right direction. So this is less than or equal to 6. This is greater than or equal to 7, which means it's less than or equal, this fraction 1 over modulus of z cubed minus 1 is less than 1 over, yeah, maybe I'll just write that here. Right? Always nice to make sure this goes in the right direction. So this is less than or equal to 1/7. There we go. Now we can say this is less than or equal to 6/7. And so now all I need is to actually compute the length of C, right? Length of C, well, it's 1/4 of a circle of radius 2 centered at the origin. Well, where it's centered doesn't matter, but it's 1/4 of a circle of radius 2. So what is this? So it's 1/4 it's 1/4 2 pi r, so it's 1/4 of 1/4 of 4 pi, right? So length of C is 1/4 of 4 pi, which is pi. Okay, and so this is less than or equal to 6/7 times pi. Okay. All right, let's do one more. Okay, so here's another example. So let say C sub r be a semicircle that is z equals r e to the I theta, where theta is between, say, 0 and pi. Okay, so it's a semicircle of some radius. And let, all right, and choose the branch of the square root of z in the following way. So we'll say that z to the 1/2 is it's e to the 1/2 log z. Okay, that we'll write as square root of r. So the square root of little r, we'll say e to the I theta over 2, where r is greater than 0. That's my modulus, and theta is between minus pi over 2 and pi over 2. Okay. Sorry, minus pi over 2 and 3 pi over 2. That's what I meant. Okay. All right. Why would I do this? Okay. Well, let's draw the picture and see. So, so first of all, if I draw my picture here, where's my branch cut, right? Where's my branch cut because of this? Well, first of all, this semicircle looks like this. Right, here's my C sub r for this thing, so from 0 to pi. Okay, but according to this, the branch cut that I've made here in defining this is the origin and the negative y-axis, right? Which misses this curve entirely, right? So this is a tactic, right? When I am allowed choice, I have a curve that say I want to integrate over or talk about an integral along. It's best if I can just entirely avoid all problem points, right? So if I can use a branch of the function that avoids that entirely and doesn't touch the curve anywhere, then I'm very happy. Okay. And so let's actually look at what I would do. So what I want to show that if I take the limit as this r goes to infinity of the integral over this curve, c sub r, of z to the 1/2 over z squared plus 1 dz, I want to show that this is 0. Now, you might say, why would you want to show that? Well, forget about that for a second. Say that I just want to know that this is the result of taking this limit. So letting my radius be huge, right, causes this contour integral of this thing to go to 0. The key thing here is I want to do this without finding the value of this integral. I want to do this without finding the value of the integral. Now you might say, well, how would I do that without computing the value of the integral? But we're in this section where we've been talking about bounding these things, so of course that's going to be the immediate thing that you think to do, right? Okay. So let's do that. Okay, let's come up with a bound here. Okay, so in order to do this, I'm going to bound both the numerator and denominator, and then we're going to see what happens there. Okay, so first of all, if I look at the modulus of the square root of z, right, z to the 1/2, just by the definition of this thing, this is the modulus of, so this is the modulus of square root of r e to the I theta over 2. Okay, which the modulus of this thing is 1, so this is just the absolute value of square root of r, which is just square root of r. Okay, so that's easy enough. And again, using my related inequality to the triangle inequality, this is greater than or equal to the absolute value of the modulus of z squared minus 1. Okay, which is r squared minus 1. Okay, now you might say, wait, like what if r is less than 1? Then this thing would be negative, and so you'd have to take minus that. So we can restrict our attention to modulus of z is r, which is greater than 1. Why are we going to be doing this? We're going to be letting r go to infinity anyway, so we're not interested in values r that are smaller than 1, right? When you think of r, since we're sending it to infinity, you should be thinking of things like, 500 million or something. Okay, and so when I say look at the modulus of the ratio, that is square root of z over z squared plus 1. What is this? Well, this is going to be less than or equal to square root of r over r squared minus 1. Okay, and that's going to be true for all z on this curve c sub r. Okay, thus the contour integral over the c sub r, or rather the modulus of this contour integral of z to the 1/2 over z squared plus 1 dz is less than or equal to this square root of r over r squared minus 1 times L, right? But what is that L? Well, L is pi r, right? So length of L is pi r. So this is square root of r over r squared minus 1 times pi r. Okay. But this quantity, what does this go to as r goes to infinity? As r is going to infinity, heuristically, you could say, okay, the power of r in the numerator here is like r to the 3/2. The power of r in the denominator is r squared. That dominates. It's in the denominator as r goes to infinity, so the denominator is going to infinity at a faster rate than the numerator, so this thing is going to go to 0. But we can actually just do the algebra here. And so if I look at, say, pi times r times square root of r over r squared minus 1. If I look at this thing and multiply by 1 over r squared, 1 over r squared, okay, to move these things around, what do I get here? I get pi over square root of r, so I have an extra 1/2 power of r here, and I get 1 minus 1 over r squared. Now, if I send r to infinity, this thing goes to 0, and this thing goes to 1. Right, so this goes to 0 over 1, or 0 as r goes to infinity. So this thing limits to 0, thus the limit. So because this thing limits to 0 as r goes to infinity, the modulus here limits to 0 as r goes to infinity, and so as r goes to infinity, that so the limit as r goes to infinity of the contour integral over this contour c sub r of z to the 1/2 over z squared plus 1 dz. This is 0. Okay. Very nice that we can compute something like that without actually having to compute the integral itself. So this is pretty liberating to be able to do something like that. Okay. And now we happen upon kind of a thing that we always have to return to whenever the question of an integral comes up, which is how is this notion of integral related to the notion of an antiderivative? And every instance of integration that you've ever been exposed to has been related to the notion of an antiderivative. So there's fundamental theorem of calculus all the way back in Calc 1 tells you exactly how integrals and antiderivatives are related. Also, going to like Calc 3, once you define things like line integrals, right, were intimately related to the notion of antiderivative. So that is to say that if you were in an instance where the thing you were integrating, so in that case, a vector field along a curve in space. So if you were integrating, say, a vector field along a curve in space, and that vector field was a conservative vector field, that is, it had, if you like, an antiderivative thing that it came from, right? It was the gradient of some other thing. Then you could actually compute that line integral in a simple way in terms of, we'll call it the antiderivative of the vector field in question. Okay, it wasn't called that; it was called the potential there. But anyway, so how does this work for us, right? So the big question is, where do antiderivatives come in? And first of all, what do I even mean by antiderivatives here? So where do antiderivatives come in for contour integrals? Okay, and so you could cheat a little. So you could cheat a little by using this fact that contour integrals are really line integrals, and so most of what you know about line integrals can be adapted to contour integrals, because contour integrals are really just line integrals if you're careful, right? And so knowing the fundamental theorem of line integrals would tell you something about how this should work for us. And so that's going to basically take care of most of our questions that we had. So in the last lecture, lecture 15, I had a list of like 4 questions about how the notions of being independent of path were related to notions about like when, say, it was true that a line integral or a contour integral of some function was always 0 around some closed contour, or around any arbitrary closed contour. Like how we were able to predict that, and what conditions we were going to be able to come up with that guaranteed us that. So first, so the answer is, well, they come in here, right? Exactly here. So first, let's define antiderivative. So what is an antiderivative for a function? Let f of z be continuous on domain D. Okay, and antiderivative of f on D is a function f prime, or big F, I should say, of z, such that f prime of z is equal to f of z for all z in D. Okay. Note, since f is continuous, and by definition big F has to have a derivative at all points of D, it means that this thing has to be analytic on D. Right? Note, by definition, big F of Z is analytic on D. Because not only does its derivative exist everywhere, it's also continuous, and this is well defined everywhere on D. Okay. Another note. Antiderivatives are unique up to a constant, an additive constant. Antiderivatives are unique up to an additive constant. How do I know this? Well, if I have two antiderivatives, here we can prove this really quickly. If I have two antiderivatives, say big F and big G of F, then we know that big F prime of Z is little f of Z for all Z, but this is also big G prime of Z. Okay, and so, for instance, the derivative of F minus G is F of Z, or little f minus little f, which is 0. And this is 0 everywhere on D, since this equality is true everywhere on D. Okay. So then we have analytic functions that have 0 derivative everywhere on D. So what does this mean? This has to be constant. And so f of Z is equal to G of Z plus constant. This is the only difference that can occur between antiderivatives for the same function. Okay, this fact is also true for, you're very familiar with this from Calc 1. Okay. Okay. And so, our big theorem here. So big theorem. Maybe we'll call this the fundamental theorem of complex functions. So fundamental theorem of complex calculus. So it says the following. So suppose that f of Z is continuous on D, which is a domain. Okay. If any of the following statements is true, then so are the others. So I should note, this does not mean that all of these are true or some of them are true or whatever, okay, for a general continuous function, okay. It means that if any of these conditions are true, then the rest of them are true. So they're either all true or all false, right? They are either all true or all false for F. Okay. So these facts are certainly not going to be true for all continuous functions F on a domain. Okay, so here are the conditions. So condition 1, f of Z has an antiderivative throughout the domain. F of Z has an antiderivative throughout D. So we'll call this antiderivative big F of Z. Okay. Now we know There are plenty of continuous functions do not have antiderivatives, right? This is exactly why integrating was hard in calculus. Was that if you screwed up even even a simple algebraic error that like altered a single exponent could take an integral from being easy and straightforward to do to being completely impossible to do, right? Because if you weren't able to actually find an antiderivative, you couldn't explicitly do some of those basic integrals, right? So we know that there's plenty of examples of continuous functions that have no antiderivative, right? In fact, pulling one out of a hat, right, you're almost never going to find one that has an antiderivative. Okay. 2. So if this is true, the following two things are also true, and really the following are equivalent, right? So these go in all directions if any of these are true or false. So the integrals of f of z along contours lying entirely in D and extending from any fixed point z sub 1 to any fixed point z sub 2 all have the same value. What is this value? So this is the integral. We can write it from z sub 1 to z sub 2 since I'm claiming this always has the same value, so I don't have to pay attention to the particular contour used. The only thing that matters is the endpoints is what I'm claiming, right? So this is big F of z is evaluated from z sub 1 to z sub 2, or big F of z sub 2 minus big F of z sub 1. Hey, this is exactly fundamental theorem of calculus if we are not talking about complex valued functions, and if this is an integral in the Calc 1 sense, right? Where big F of z is the antiderivative in statement 1. Okay. All right. And then lastly, maybe before I go on, we already saw an example of this, right? Let me dig up the sheet. So we saw an example of this previously. I'll just have to dig up my sheet where we actually did this. So where's my... Well, now I'm having a hard time finding it. Oh, these are all from today. Let me... Some of these are... Here we go. Okay. So, our previous example, where we were integrating along contours z dz, right? And we found, oh, this was actually, it didn't matter how we did this, right? We would end up with the exact same, this was just terminal squared minus initial squared over 2, right? It didn't matter what curve we took. The only thing that mattered were the endpoints themselves, which of course meant that if this was any closed contour and the endpoints, the terminal and initial endpoints were the same, this was just 0. Okay. So we've already seen an example of this, and of course now, if this statement is going to be the case, notice that this is going to be true if this thing has an antiderivative throughout D. Does Z have an antiderivative throughout whatever domain I'm talking about this contour lying in? Well, what is its antiderivative, right? Z squared over 2. Right? Z squared over 2 does it. In fact, notice the the correspondence between that antiderivative z squared over 2 and what you end up getting here, right? That's exactly what happened. Okay, we got exactly this fact. Okay, so we didn't just do these earlier examples for no reason. This is exactly why we did them. Okay, to illustrate this. Okay. And then lastly, touching on a point that was also mentioned in that example, the integrals of f of z around closed contours lying entirely in D all have value 0. Okay. Well, this fact is pretty easy to see from 2, just because if 2 is true, right, then around a closed contour, z1 and z2 are the same, right? So z sub 1, z sub 2 are equal, and so this would just be big F of z sub 2 minus big F of z sub 2, which is going to be 0, right? And so we see now the connection here, right? So 2 is the very nice computational thing that allows us to do this if we have an antiderivative. But we have a quick statement here. If little f has an antiderivative throughout D, then the integrals of little f around closed contours lying entirely in D all have value 0. So this theorem answers in a huge way a lot of those questions that we had previously. Now, we are also going to have further statements that answer some of those questions in a slightly different way, but this provides us with one question. That is, if f has an antiderivative, right, we have this nice fact of being able to compute these contour integral really, really easily. Okay, and the other thing that this tells us is that, if it has an antiderivative, then this answers the question of one condition that we can have on a function that guarantees the contour integral around closed contours is 0. Okay, so this is one such condition. It's not the only one, though, okay, as we'll see. So there's another big named theorem that gives us another way of getting 0 around closed contours. Okay, so again, not every f that's continuous on a domain has an antiderivative. Okay, but if it does, then you get these other two facts, and so we have really, really nice ways here of being able to compute this. In fact, what's so awesome about this is, right, we don't have to use the definition of contour integral if we know that this thing has an antiderivative. So, quick example to use and abuse this. Note the function f of z, which is z squared, has antiderivative big F of z, which is 1/3 z cubed, right, on all of C, right, all of the complex plane. Okay, thus, for instance, if I am computing a contour integral along any contour that goes from, say, 0 to 1 plus I, right, of z squared dz, I can compute this using statement 2 in that theorem. So this is 1/3 z cubed evaluated from 0 to 1 plus I. And so this is 1/3 times 1 plus I cubed, which I can simplify to being 2/3 times minus 1 plus I. Okay, and this is true for every contour from 0 to 1 plus I. All right, why is this so nice? Well, I don't have to tell you that since you're doing this in a way that only depends on the endpoints, right, the specifics of the contour used don't matter, which means I don't have to worry about the parameterization of my contour, right? I don't have to worry about that at all. That doesn't even enter into this, okay? So that's an entire thing that I can just ignore, right? And that can be pretty nasty, right? Some of those parameterizations can be nasty. I could give you a really, really, I mean, I could use just an absolutely crazy curve here, right? That is still a contour going from 0 to 1 plus I, and rather than, here, right? Like, here, let's just do 1. So here's 0. 1 plus I is here, right? So there's 1 plus I, here's 0. What if I had a curve, right, that did a contour that did this kind of thing? All right, there, here's my C. Okay, but it went like this. From 0 to 1 plus I. Okay, there's my contour. Well, it doesn't matter, right? Then all I know is that the contour integral along that contour of z squared dz is still 2/3 times 1 minus 1 plus I. Yeah. Okay, so super duper nice. Okay, this is really, really nice. Okay. All right. Here's another quick example to show the usefulness of this. Let f of z be, say, 1 over z squared. Then this is, little f is continuous everywhere except the origin. It's continuous everywhere except z equals 0. Has antiderivative, and big F of z, which is, so you know exactly what I'm going to do here. This is minus 1 over z. Okay, so big F, which is minus 1 over z, is the antiderivative. When I say the, I mean, yes, I could have a constant here, but I don't care. So this is the antiderivative of little f on the domain modulus of z is greater than 0. Right, so everywhere except the origin. Okay, so that's everywhere except the origin is deleted. Okay, thus, if I look at the contour integral along any contour that I want, that say doesn't touch the origin there, right, then I'm good to go, right? So thus the integral, let's make C, so let C be a contour we could just choose it, say, positively oriented circle around the origin. But it can be any contour that just doesn't intersect the origin, that goes, say, around the origin like this. So let C be a contour, positively oriented circle about the origin. But it could be just a contour around the origin as well, of 1 over z squared dz. Well, this is 0, right? Because this is a closed contour. And again, I chose a specific one here, but I didn't have to. I could have just picked any closed contour around the origin. This would have been the same story, right? Okay. All right. So, there's a warning here. And this warning may be where I kind of stop, and we'll start here tomorrow. So warning. Put a little star here. Let's try to do the same thing. Let's try to do the same thing with f of z, which is 1 over z. The problem can't do this in the usual way. Why? Well, what is going to be our big F of z? What is going to be the derivative of, or what is going to be the antiderivative of little f here? So we know that this antiderivative is going to be, well, or it should be rather, log z that we've chosen a branch for. There's an issue here, right? So along a branch, this derivative is 1 over z. So along any branch, big F prime is 1 over z. But, and this is a big key thing here, this is not differentiable because it's not even defined along any branch cut or at a branch point, right? F of z is not even defined along a branch cut. Thus, is certainly not differentiable there. So if this branch cut, so if C crosses this branch cut, then I can't proceed. Okay. So the reason why I wanted to note this particular example is that say that we wanted to, so let's take C for instance to be a positive oriented circle. Around the origin, right? And I want to compute this thing. Okay. Well, you might say, wait, you've already computed this thing, right? And I have in another way, right? But now I want to see how that meshes with what I've done here. So how can I compute this contour integral? The problem is that this antiderivative, right, is going to be undefined along some branch cut. So it doesn't actually matter where my branch cut is, right? Say that it's even here, right? I get creative and here's my branch cut. This doesn't matter where this thing is. If this is here, here, whatever ray is defining this branch cut for log z, it doesn't actually matter because this circle is going to intersect it. Okay, and so I have to address that. Okay, I gotta make sure that I have a way of dealing with when I encounter a situation like this. So this is the other instance of where we have to consider branch cuts that I mentioned before. So notice, right, that 1 over z has no issue with this branch cut. It has an issue here at this branch point, the origin, but other than the origin, it has no issue with any other point in the plane, right? 1 over z is fine everywhere else, okay? But it's not that 1 over z, the integrand, has an issue there. It's that its antiderivative has an issue there, okay? So this is another complication that comes up if you're wanting to use this theorem to do this. And we're going to see in the next lecture how you can do exactly that, okay? All right, so that's that. So I will see you all again very soon, and we'll see exactly how to deal with it.